we'll go from the current slide. All right. All right. Curry doubles the class size. All right, we're just about to get started. Any questions or anything we've done so far? No? None? Okay. Or was it?
What section?
Oh, we're on in Chapter 4, Higher Order Differential Equations, Section 4.3, Homogeneous Linear Equations with Constant Coefficients, and we just finished talking about it ad nauseum almost, and now we're getting ready to do example 1. Okay? Now, and we might do a quick, I don't do anything quickly, a little review, if necessary, on the various cases. So here's example 1. Let me get my pen set up. All right. Solve the following differential equations. Here's the first one. 2y double prime minus 5y prime minus 3y is equal to 0. Okay? Now, linear, second order, ordinary differential equation with constant coefficients. Nice form to have. What's our first assumption? And by the way, if you haven't noticed this already, once you get into second and higher order differential equations, separation of variables basically becomes a non-entity. I mean, because you got multiple derivatives and stuff, that would be a very difficult thing to do. So our easiest technique is now out of the picture. But this is a pretty easy technique too. What's your assumption, or what's your approach? If it's factorable, not yet. I know what you're leading to, but this is a differential equation. Factoring it doesn't really do a lot of good because, something... Say again? Okay, we're going to get there. But what were you thinking of factoring? This or something like it? Okay. The thing is, factoring means things are multiplied together. And you see, you don't really multiply y primes by y double primes and other things like that. So y double prime, 2y double prime is not 2y double prime times y double prime. Okay? That would be 2y double prime squared, and that would be linear. I think I know where you're heading, but you're skipping a step. Okay, let's go back to this question. What function that you can think of can you combine the function, its first derivative, its second derivative, and all its derivatives together and have them make sense? In other words, what's function's first derivative is very similar to the function, and second derivative is very similar to the function and the first derivative? E. Okay. Does that ring a bell? We'll let y, you don't have to do this, but we'll do it for right now. Let y equal what? Sort of a generic form. E to the what? Okay, let's be a little more general than that. I don't think those coefficients. E to the what? Mx. All right. Now, is this beginning to ring a bell? Remember? All right. What's the next step? Then, y prime is? Either one. Huh? M e to the mx. And y double prime? M squared e to the mx. Now we plug these things back into the differential equation. 2m squared e to the mx minus 5m e to the mx minus 3 e to the mx is equal to 0. Now, what you notice about that equation, now this is an algebraic equation. That was a differential equation. This is algebraic. What you notice about it? Every term has e to the mx in it. Okay? Is that? And the whole thing is equal to 0. So you could factor out the e to the mx. And let's do so. Okay? E to the mx. And what is left? 2m squared minus 5m minus 3. That's equal to 0. Now we have a product of two entities. This times that is equal to 0. That tells us that either that's equal to 0 or that's equal to 0. Zero product principle. You've got two things multiplied together. The product is 0. One of those has got to be 0. Is e to the mx ever 0? No. Okay? If m is positive, it's like this, but never reaches 0. If m is negative, it's like this, but never reaches 0. Ever. Okay? So therefore, we can divide that out because it can't be 0. Okay? Now we get to what you were looking at. And this is called the auxiliary equation. And basically, as soon as you see a linear, higher order differential equation with constant coefficients, if you want to look at that and immediately go to the auxiliary equation, you can, because it's going to happen this way every time. Now your question is 2m squared minus 5m minus 3 equals 0. How do you solve that? Factoring it, okay? And how would you suggest factoring that? Okay, 2m, and you've already decided it's going to be a plus 1 and a m minus 3. Let's see if that works. Anytime I factor, I always check and see. 2m times m is 2m squared. That works. 2m times minus 3 is minus 6m plus m minus 5m minus 3. Perfect. What does that tell us? Either if you can do it right there, m is equal to negative 1/2, or m is equal to 3. Now let's go back and see what difference that makes, okay? Your solution then will be, this is one solution. You got two values for m, second order differential equation. You know you're going to need at least two arbitrary constants, right? So your y now is going to be c1 e to the minus x over 2, or minus 1/2 x, however you want to write it, plus c2 e to the 3x. There's your general solution. Two arbitrary constants because it's second order. No boundary or initial conditions, so we leave it in general form. Make sense? That's the superposition principle. You got one solution with minus 1/2 for m, the other for 3 with m, so you're going to have a linear combination of the two. And those are linearly independent, almost by definition. E to the minus x squared, x over 2 goes like that, e to the 3x goes like that. No way they're dependent on each other. All right. And that's their solution as well. C1 e to the minus x over 2 plus C2 e to the 3x. All right. Let's go. Any questions on that before I delete it? Okay. Let's go to another one. Here we go. I've lost it. Y double prime minus 10y prime plus 25y is equal to 0. Okay? What's going to be your first step? Second? Okay, that is our first assumption. Y is going to be some form of e to the mx. Now, do you need to go through all the steps, or you want to go straight to the auxiliary equation? Okay, and what will the auxiliary equation be? M squared minus 10m plus 25 equals 0. Okay? Now you can go through the others. That's perfectly fine. There's nothing wrong with it. Just implants it in your head how we got here, or you can go straight here. Now, what will you do with that? Factor it, and how will that factor? M minus 5 times m minus 5. Very good. And that's equal to 0. What does that tell you? M is equal to 5. Whoops! Okay, we got a problem, Houston. We only have one potential solution, and we need two, because this is a second order. You remember the rule when you, and I don't know if you recall from the last time, this was a condition where your discriminant of your, if you did the quadratic formula, that b squared minus 4ac was going to be 0, giving you only one solution. How do we deal with that? What's the second solution?
Does it have anything to do with the derivative?
Say again?
Does it have something to do with the second derivative?
Not really. It'll all have to fit that, but there was a rule, and it's, if you turn and look on the previous page, we just did case 1, distinct real roots. That's what we did in the A part. This is a repeated real root. In other words, this is m equal 5 and m equal 5. It's really two roots, but they're the same number. So what do we do? What's our second solution? You're absolutely right that one solution, we'll call it y1, is equal to, and I'll even put a parenthesis, c1 e to the 5x. But we got to come up with a second solution.
So plus c2 5e, plus c2x.
Yes, that's what we do. Plus, okay, then we'll take off the 1 here, c2x e to the 5x. That's what we do with repeated roots. We just multiply x by that exponential form. Now, if you have any doubt about it, by all means, go back and take the first derivative, the second derivative, and add them together and see if you don't get 0. And you do. Okay? So that's the technique when you have multiple roots. Okay? Good? Now, let's go to any questions. Do I need to leave this up a little longer? Okay? Let's go to the C part. Okay? Y double prime plus 4y prime plus 7y is equal to 0. Okay? Where are we going to go? Okay, and what would that be? M squared plus 4m, second, plus 7 is equal to 0. Now this is remembering that it's coming from y is equal to e to the mx. Just, I like always to write it down so I don't get bogged down in this and forget, why am I doing this? Okay. Now, what are you going to do with that? Quadratic formula, because that one will not factor at all. So the quadratic formula tells you that m is equal to what? Okay, minus b plus or minus the square root of b squared minus 4ac all over 2a. So let's plug in what those are. Minus 4 plus or minus the square root of 16 minus 28. Any bells going off yet? Over 2. Okay, any bells and whistles, warnings, flashing red lights? All right, so that'll be the square root of negative 12 over 2, which, by the way, would be minus 4 plus or minus, can you pull a, you got to pull two things out. Second? Okay, 2I root 3, right? Okay, over 2. Well, that 2 will go into 4, or minus 4, minus 2 times, and it'll go into 2 one time. Okay? So now your solution is minus 2 plus or minus, I like to write it I root 3. There are some books that insist on writing it in standard form, A plus or minus B I. I don't like to do that because if you move the I over here and write it a little too close, you think it's under the radical, or you're not sure. Put it in front, it's obviously not under the radical. Okay? So I'm okay with that. In fact, I like that. I believe this book nope, it puts the I on the other side too. I just, maybe with typeset where you can line it up and see for sure, but when my lives are writing and stuff like this, I want to put it there so I don't get confused. What do we do with this? Sine and cosine. And that's the case 3 that we had. And it's actually, the result of this is just above this example as equation 8. So what will it be? Y is equal to, it doesn't look at all like the e to the mx, or not much like it anyway. What do you get there? Okay, it does have that in it, e to the minus 2x. Okay, that's from the real part of the m. Okay, and what's so that? C1 cosine. Say it again. Okay, it's just root 3x. Okay. Hey, here's Lauren. Increase the class size by 50%. Okay. Okay, I know you're in here. There you are. All right. Oh, and by the way, I should wait till more people come in, but let me be sure to say this. I've already had a minor discussion about it, and here's one more, okay? This, obviously, my best, highest level class this summer, I have received one paper in, research paper in. That's what the discussion was about earlier. And I have received all your test 1. Have I given all of you your test 1 back? Okay, good. Okay. Don't have any of the test 2s yet, but I'm sure you're working hard on them, right? Okay. And then, however far we get in chapter 4, and if we do creep into the next chapter, I don't remember if that's 5 or if we skip 5. 4 is such a long chapter, we seldom get there. Now I think what we do then, if a little bit of Laplace transforms, that's 7. But right now I'm not sure we're going to even get there because there's so much to do in this chapter. This is the bulk to me of differential equations. This chapter we're on right now. 2 was part of it, but then 3, or whatever the one we did before, 3 was part of it, and then 4 is the biggest part. So, it's just and you see what goes here as the coefficient of your variable. See, your real part goes in the e part, and your imaginary part goes in your sine and cosine. So what's the second part of this? Plus C2 sine root 3x. There's your solution. Okay? And that's the form that your solution will take anytime your discriminant comes out negative. Discriminant comes out positive, you have two functions. You have the C1 e to the blah x plus C2 e to the other blah x. Okay? If the discriminant comes out 0, you have C2e to the blah x, C1 e to the blah x plus C2x e to the same blah x. And if you have the discriminant coming out negative, you have e to the blah x, the real part blah x, times C1 cosine imaginary part x plus C2 sine imaginary part x. Okay? Make sense? And by the way, that was Euler's formula, which was an incredible, we used Euler's formula to get there, an incredibly powerful, insightful, unbelievable type formula. Now, he has a couple of others that are even more amazing. Let's see if I can remember it. You might check me on this and see if this is right. E to the minus I pi is equal to negative 1. I think that's it. I'm not absolutely certain, but I believe it is. Because if you put a pi in for your theta, that'd be cosine of negative pi. Yeah. Cosine of negative pi, would be negative 1 plus I times the sine of negative pi. Well, sine of negative pi is 0. So sure enough, that's equal to negative 1. Now, that's a sort of a simple result of Euler's formula, except, think of this, in that one little thing, a term on one side, a term on the other side, you have every unusual feature in mathematics that we deal with every day. You have the irrational number e, the base of our natural number system. You have the imaginary unit, I. You have the other irrational number that has to do with all kinds of trig stuff, circular stuff, anything else pi, and you have a negative 1. So you have a rational number, two irrational numbers, and an imaginary number, all in one concise little form. Pretty amazing. That's also sometimes called Euler's equation, I think it is. Pretty amazing in some senses. For a mathematician, maybe for an engineer, they say, so what? Okay, I don't know. All right, let's move on to example 2. These 3 examples, you left the C's in there. If you have an initial value problem, you lose some of the C's. Hopefully all of them, okay? So let's do this one. 4y double prime plus 4y prime plus 17y is equal to 0. Under the conditions that y of 0 is equal to negative 1 and y prime of 0 is equal to 2. Now, let me go back to remind you what makes an initial condition. I mean, pretty simple stuff. This one really, to me, looks like a true initial condition because you're taking the value of 0, which you think of as the first value. So y of that has to be some value, and y prime of the same x value has to have some value. Okay? If these two numbers were different, then we call that a boundary condition. Or if you had y of 0 and y of 1, that's a boundary condition. Okay? To be an initial condition, number 1, whatever your degree of your differential equation is, the order of it, you've got to have up to, but not including that order of initial conditions. So y of some value equal to something, and y prime of the same value is equal to something, up to, but don't get to y double prime. So that's true as an initial condition problem. Just a little bit of review there. All right, where would you head for this one? 4m squared, going right to the auxiliary equation plus 4m plus 17 equal to 0. Now, again, I like to remind myself, we're assuming y is equal to e to the mx. That's where that came from, okay? Now, any thoughts on that one? It's going to be a negative square. Yeah, the discriminant's going to be negative. You want to go straight there? You really need the real part too, so we need to do the whole shebang. So start shebanging. M is equal to minus 4 plus or minus the square root of 16 minus. And you tell me. I don't know it either. 16 squared is 256, I think, and another 16 multiplied by that, added to that is 272. I think that's right. Someone do it on a calculator. See if we're thinking right. Yeah, I think that's right. Okay, over what?
72.
8. Okay, because it's 2a. All right.
It's minus 2AC, right?
Huh?
It's minus 2AC, right? 4AC, my bad. Okay.
Yeah. All right. And here's Rod. All right. And again, I've been reminding everybody of this. Research papers, I've gotten only one in. And guess what, folks? You only have 1 weekend left before they're due, okay? So if you were planning to do it on the weekend, this is it, okay? Now, you can do it any day of the week you want to, but weekend usually gives you a little more free time. And also, start getting your second test in. Has everybody got the first test back? Okay. So start getting the second test in and the paper in, because on Thursday of next week, 1 week from today, I will be giving you your last test, the Chapter 4 test, okay? And that last test will be due back in sometime the next week, okay? Now, if you want to get it to me Monday, it's not necessary, because technically Monday's still a class day. But Tuesday, Wednesday, or Thursday, I'll take it any one of the 3 days. Now, I can't recall what they said about whether we're going to work that first Friday in August or not. The Fridays off, school closed on Fridays, was supposedly only for June and July. Well, we worked the first Friday in June. I can't remember if we're going to work the first Friday in August or not. It doesn't matter, because I've got a treatment that Friday, so I'm not going to be on campus whether we're working or not working. I've got a treatment, and it starts at 8 in the morning. I'll have to be there for labs at 7, and I'll be there all day. Always am there all day. So there won't be any way that I'll be here on Friday. Now, if the school is open on Friday, and you want to turn in that final exam on Friday, you can slide it under my door, and when I come in Monday morning, it'll be there for me. I'll grade it and get your grades in. Because you see, grades are due in by noon on Monday. So I don't have a lot of leeway there, okay? I can't accept work at 11:30 on Monday and expect to get it graded and averaged and everything done with it. You're going to get an incomplete. Then I'll grade it and average and change the incomplete to a grade, but you're going to get an incomplete to begin with. So don't do that, okay? Because I got 6 classes, and if 1 or 2 people in each class, bring in stuff late, no way I'm going to be able to get things graded in time. So please get the papers in next week, your second test in next week, and I'll be giving you your last test next Thursday, 1 week from today. All right, enough of my commercial. Let's go on. Where do we go from here? Did you check that and verify that that's right?
Yeah.
Okay, good. All right. Now, what does this come up being? Minus 4 plus or minus the square root of, and what's that? I believe that's 256, isn't it? Negative 256. Because we added 16 to it, that's how we got 272. Now we're subtracting it off, okay, over 8. And we just said that 256 does happen to be, it's minus 4 plus or minus. Isn't that a perfect square of 16? 16i, right? Over 8. And we can simplify that a little bit, can't we? What will that be? Negative 1/2 plus or minus 2i. So what's our solution? Y is equal to e to the negative 1/2 x c1 second cosine 2x plus c2 sine 2x. Very nice. Except we have some initial conditions. So let's plug those in. Y of 0 is equal to negative 1. Right? I did copy that, right? Didn't I? Yeah. So that's supposedly equal to e to the and you plug in 0 for x, e to the, help me, plug in a 0 for the x. E to the 0. What's e to the 0? Huh? 1. Okay, so we don't need the e there at all for this one. Okay, so we have, it boils down to C1. What's cosine of 2 times 0? Yep. 1. So that's just a C1 plus, what's sine of 0? 0. You don't have anything there. So forget the plus sign that I started to write. So guess what C1 is? Negative 1. Got that one done. So let's go back to the original. Y, okay, of x is equal to e to the minus x over 2, that's just easier to write, times minus 1 cosine, so let's just make it minus cosine 2x plus c2 sine 2x. That's all we know right now. And what do we need? What's the next thing we know? Your y prime. So let's plug in what? Let's take our first derivative. Y prime of x is equal to, okay, I'll buy that, e to the minus x over 2 a little louder. Yeah, it's a negative 1. I just didn't like writing a 1. I just put negative cosine, so I did. Okay, so that would make it a sine 2x. Okay, if you haven't picked up what he's doing here, it's a product rule, right? The first times the derivative of the second. And that's the first part of the derivative of the second. What's the second part of the derivative of the second? Plus C2, second, cosine 2x with one little other. 2, because chain rule, right? Chain rule on the 2x. Okay, so there's your y prime of x. No, it isn't, because what have we not done? We haven't done the other part, so let's do the other part, and that will be all right, yeah, it's going to be a negative, not a plus. It normally would be a plus, but it's 1/2 e to the minus x over 2 times this thing right here. I don't have room to write it, okay? So that's the second part just like it was. Oh, man. I need more room to write. So what I think I'll do, I wish I'd have started that line way over here. So what I think I'll do is erase this part because I've already used it, I think. And maybe not. Well, I don't need this anymore. We got that, right? So let's take this one out. And we probably don't even need that one anymore either. Okay. All right. All right. Okay. So I'm going to write that line over again. Y prime of x is equal to e to the minus x over 2 times sine 2x plus 2c2 cosine 2x minus 1/2 e to the minus x over 2 times minus cosine 2x. I can't write this morning. I don't know what. Plus c2 sine 2x. Okay. Let me see if I can make this look a little bit better. Okay. All right. Now, I guess there's probably some way you can simplify that a little bit. Because here you have a e to the minus x over 2 sine 2x. Let's leave them alone. Let's just plug in y prime of 0. What's y prime of 0 got to be? 2. So let's plug in a 0, and what do we get? E to the 0 is? So that's equal to 1 times, what sine of 0? And sine of 0 is? Okay. 0. Exactly. Remember how sine looks. It starts at 0 and does like this. Cosine starts at 1 and does like that. The sine of 0 is 0. Okay? So that part goes to 0 here. And then you have a 2c2. And what's cosine of 0? 1. Okay? So that's by itself. Minus 1/2 of x is 0. E to the 0 is 1. Okay, so that's just a 1 times, what's cosine of 0? So that's a minus 1 there, plus, and then c2 times 0. So no plus there at all. Okay, now that turned out pretty simple, didn't it? Hopefully I did it right. So this tells us that 2 is equal to 2c2 plus 1/2. If I did it right, that's what that leads to. So let's multiply everything by 2. That would be 4 is equal to 4c2 plus 1. So that would be 3 is equal to 4c2. That means c2 is equal to 3/4. All right. Before I get too carried away here. Yeah, okay, I think it's going to turn out okay. Now let's go back to our original function. And I think I can erase these lower ones now, if I can get the eraser to come up. There we go. I don't think we need these anymore. I hope not anyway. If we do, I'm in serious trouble. Okay. But y'all got it all written down, I can tell. So what's our our exact solution, or okay? Sorry to keep repeating this, but I think it's important. Research papers are due next week. So far I've gotten only one in from this class. I'd really love to have your second test in sometime next week, okay? And next Thursday I'll be giving you your last test, okay? You've got to get that back to me the following week. I mean, you don't got to, because I can give you an incomplete, but I don't think your home school is going to really appreciate that too much. If you need to register stuff that depend on this, maybe you don't. But that's why please don't wait and plan to do the research paper test too and the other thing in the next weekend. I don't think that's going to work too well for you, and you're not going to be your family won't like having you around. I don't think, if you're that stressed. Okay, so try to get everything in next week. So, and by the way, did I return to everybody your first test? I think I did. Okay. So get your paper and your second test in this week if possible. I mean, this coming week if possible. If you can't get it in today, very good. All right, thank you so much. Okay. All right. So, I marked you here. So let's get back to this. Here's our final answer. Okay? Because we do have initial conditions, we don't need any arbitrary constants. So now our y is equal to e to the minus 1/2 x, or x over 2, however you want to write it, times, and that was a minus cosine 2x plus 3/4 sine 2x. That's it. Okay? I think that's what we got in the book. E to the minus x over 2, it doesn't matter how you write that, times a minus cosine 2x plus 3/4 sine 2x. Now, I find sort of interesting their next sort of subtopic here they put in all caps, green print. It's just sort of interesting. 2 equations worth knowing, okay? As if, yeah, you need to remember these. Here's one. Y double prime plus k squared y is equal to 0. Okay? Where k is real, not complex. Okay? The second one is y double prime minus k squared y is equal to 0. Okay? They look pretty similar. They are fairly different. Okay? The first one has no real roots to your auxiliary equation, right? M squared plus k squared equals 0. Ain't no way that's going to be true in the real number system. So you have to go to the complex number system. So your solution is y is equal to k1, and I'm sorry, they do c1, sorry. Used to the old German influence. c1 e to the kx plus c2 e to the minus kx. No, so I'm looking at the wrong one. I said that can't be true because this is sines and cosines. C1 cosine kx plus C2 sine kx. Okay. Now, the second one has solutions. M squared minus 1 equals 0. M's equal plus 1 or minus 1. So that's simply y is equal to C1 e to the kx plus C2 e to the minus kx. Okay. Now, here they do this sort of crazy thing they've done before. Notice that if we choose C1 equals C2 equal 1/2 in the second equation, we get a particular solutions of 1/2. This is what they're going for, and so therefore I'm not too happy with it. If both C1 and C2 are 1/2, then what we have here is e to the kx plus e to the minus kx, which, if I'm not mistaken, and so I might be, is the hyperbolic cosine or sine? It's cosine, I think. Yes. Okay. Yeah, hyperbolic cosine. Now, if, however, C2 was negative, then you'd have hyperbolic sine. So this one would be hyperbolic cosine of kx. Okay, and if this is with C1 equals C2 equal 1/2, and if C1 was 1/2 and C2 was negative 1/2, then you have hyperbolic sine. Okay, so, well, since hyperbolic cosine and hyperbolic sine are linearly independent on any interval of the x-axis, an alternative form for the general solution there would then be y is equal to, now they go back and put in C, so it sounds like they're going in circles, and it really does feel like that. C1 hyperbolic cosine kx plus C2 hyperbolic sine of kx. Now they don't put parentheses around the kx. I did. It doesn't matter. Now, I think this is why they're saying this. Look at that. This is the regular sine and cosine, and that's your hyperbolic sine and cosine. Yay! I mean, so what? I mean, I don't know. There's really no connection between those, except that the derivatives act a lot alike, but not the same, and other things. So I don't get a lot of jollies looking at that, but maybe you do. So if the plus sign gives you your cosines and sines, and your minus sign gives you hyperbolic cosines and sines. And frankly, any day of the week, give me the e's. Okay? I don't care about the hyperbolics. Give me the e's. They're so much easier to work with, so much less to have to remember. But anyway, two equations worth knowing. Okay. Now, what if we had higher order equations? Okay. I hope you can imagine what's going to happen there. So let's say you had an a sub n. Now remember, we're dealing with constant coefficients now. Then your auxiliary equation would be a sub n m to the n plus a sub n minus 1 m to the n minus 1 plus a sub n minus 2 m to the n minus 2 plus dot 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 plus down to a sub 3 m cubed plus a sub 2 m squared plus a sub 1 m plus a sub 0 equals 0. Okay, so here you have a big, long, hairy polynomial equation. Now, if you remember from algebra, and we already have demonstrated, quadratic equations are solvable. Just about always. I mean, if that discriminant is positive, you get two distinct solutions. If it's 0, you get a repeated solution, we know what to do with that. And if they're negative, we get the sines and cosines with an e involved, and we know what to do with that. Okay? But when you get up in higher order algebraic equations, they're not always solvable. Okay? They're not always factorable. There's no cubic formula. There's no quartic formula. You're kind of lost sometime, and you have to go back to your algebraic techniques to try to find roots, find zeros, and they all work, but they're not guaranteed to work. Okay? So it just makes the problem a lot harder. Okay? Now, if all the roots of those m's, if you can factor or solve or however you get it done, and every one of those has a distinctly different root, you have n distinctly different roots, then you know what your solution is. Y is equal to C1 e to the m1 x plus x, C2 e to the m2 x plus C3 m to the e to the m3 x plus dot 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 plus c to the n minus 1 e to the m to the n minus 1 x plus c to the n e to the n x, m sub n x. Okay? There's your solution. If every one of those m's has a uniquely different solution, okay? M1, M2, M up to Mn, there it is. Okay? Now, what if one of those m's, though, okay, let's say this one, when you got around to solving for that, however you did it, you came up with m equal 7, m equals 7, m equals 7, okay? What do you do with that? Well, if that was the one in here, that the m sub n minus 2 was that, there were 3 of them, then when you got up to that one, then you would do a c1 e to the 7x plus c next c x m to the 7x plus c to the next c x squared m to the 7x. You just multiply another x for every multiple you have there. Okay? So if you have a multiplicity of 5, what will your x powers of x go up to? They go up to 4. So the first one's just going to be e to that, and the next one x e to that, next one x squared e to that. Yeah. So if you add 5, you go up to x fourth. E to the same m. Okay. Now, what they don't tell you here, but what it'll come down to, I'm almost certain, trying to think if this will really be true. As long as your A's are real constants, and that's what they're assumed here. A's are all real. No complex constants. All real. Then you're going to come up with every one of your solutions to that, if you have any complex solutions, m being, the A's are real, but the m's could come up being complex. They always show up in complex conjugate pairs. So you'll always be able to do a factor of sines and cosines from that. Okay? You could have multiple complex conjugate pairs. That's okay, but they'll always be in pairs. So let's do example 3. Somewhat simple, just a cubic, not an nth. Okay? So here we have a y triple prime plus 3y double prime minus 4y equals 0. Where do you start? Anybody? Where do you start? Anybody? Make a guess. Second? Yeah, okay. She's starting with her auxiliary equation, which will be m cubed plus 3m squared minus, no m, minus 4 equals 0. Okay? Now, I also, just because I'm sort of anal retentive, I guess, always like to put y is equal to e to the mx. That's what the m is standing for. Just to remind myself later, that's where it came from. Okay? Now, that's not an equation I can factor. It's not a particularly fun equation. However, it does have one really nice feature about it. Does anyone see that? It's always the first thing I do when I have a higher order equation with constant coefficients, polynomial equation. One of the first things I do is say, what if m was equal to 1? What does that tell you? What if m was 1? What do you get? 0. There's a solution. M equal 1 is a solution to that. Now, I kind of lucked into it by always looking for that first. That's the easiest m to test. M equal 1. M equal minus 1 is just a little bit harder, but it's not too hard. The rest of them get a little bit worse. But m equal 1 is so easy. So we have a solution. M is equal to 1. Now, how does that help us? It really does, but it's not immediate, because since you know m equal 1 is a solution, you can use, do you remember the good old synthetic division? Put that 1 on the outside. Oh, no, you don't. And what do you put on the inside? Anyone recall? Your coefficients. Okay, now be sure you're in descending order of your powers, and we are. So that's going to be a 1, 3, 0, negative 4. You have to account for every term. And you're missing an m, so you put a 0 in. Here's a little key that I do here. Look at the degree of the polynomial. You better have one more term here. Okay, one more number there in that degree. And we do now. Okay? Now, the next rule is one I make up. It's skip a line, draw a line. Okay, that's pretty easy, isn't it? And then you bring down the 1. And then do you remember what to do from here? 1 times 1 is 1. No, you just add, yeah. 4. 4. 4. You're stuck on 4s, aren't you? 4. 0. Ding, 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 ding. It better be a 0. Okay? Otherwise, that wouldn't have been a 0. Okay? We already knew that was going to be a 0, didn't we? Yes, but we needed this. What does this represent? What does this represent? Your cubic equation. What does this represent? The quadratic quotient of dividing m minus 1 into this. That's what you get, a quadratic quotient. So make that a quadratic. What is that? Now you put your m's back in. You took them out here, you put them back in here. Help me. Help me. I need help. M squared plus 4m plus 4 equals 0. Now we're down to a quadratic. Once you get to a quadratic, don't use synthetic division anymore. You know what to do. Either factor, which you can't, right? Or can you? Yeah. Wait. Yeah, okay. And so what does that give you? M plus 2 squared, right? So what does that tell you? M is equal to negative 2 or negative 2. All right, you got your three, goodness gracious. Okay, I'm trying to say your 3 roots, and I write 3 down. Okay, your 3 roots, m equal 1, m equal minus 2, and m equal minus 2. So can we write down what our solution is? Y is equal to, bless you, C1, what do you say? E to the x plus C2 e to the minus 2x plus C3 x e to the minus 2x. Anytime you have a double root, then your e to the mx is going to be one solution, x to the e to the mx is going to be your second. If you had a 7-tuple root, you're going to have x squared, x cubed, x fourth, x fifth, and x sixth, you know, with e to the mx on it. Yeah, good deal. There's your general solution. Make sense? So y is equal to C1 e to the x plus C2 e to the minus 2x plus C3 x to the x e to the minus 2x. I can't get that said right. Okay. All right. Anyone in favor of a quick break? I think I am. We'll come back and start example 4. Do I need to leave this up a little longer? Okay. Let me, okay. All right, good. Thank you so much. Okay. All right, example 4. Here's a 4th order differential equation, again with constant coefficients. d4y over dx to the 4th, or that's what it looks like anyway, plus 2 d2y dy dx squared, okay, plus y is equal to 0. How do you begin a problem like that? Your auxiliary equation. Now this, again, I'd like to remind myself, you're going from y is equal to e to the mx. When you have constant coefficients, linear, ordinary differential equations, that's what we use. Okay? So what's your auxiliary equation? M to the 4th. Got it. What do you do with that? Any ideas? Guesses? Approaches? Where would you head? Don't need to talk with your algebra teachers, I think. Factor it, okay? How does that factor, or does it factor? Say again? M squared plus 1 squared, right? That's equal to 0, okay? Which is m plus 1. M squared plus 1 times m plus 1. M squared plus 1, if I could talk. Okay? Absolutely. But, where do you go from there? Yeah, you got it down to quadratics, but we still need solutions for those. What are your solutions for m squared plus 1? What values of m make that true? Any? What value for m would make that in the parentheses equal to 0? Say again? Hint. No real number. Still no suggestion? Say again? I. You're stuck on yourself. Oh, no, never mind. Okay. This would be m is equal to plus or minus I. Because if you put an I in there, I squared is minus 1, plus 1 is 0. And if you put a minus I in there, minus I in parentheses squared is still I squared, plus 1, minus 1 plus 1 is 0. Absolutely. But that itself is a double root, okay? So we're going to have to be careful with this. So what does this suggest to you? What is your solution in this kind of form? Y is equal to? Now, just a couple things to note. There is no real part. The real part is 0, right? So therefore, your e to the alpha x is e to the 0, which is 1. So there is no e part in this one, okay? And where would you start then? And maybe I don't need a parentheses there, so I'll take it off. Where would you go? Okay. 1? Is that what I heard? C1. Okay, that's what I thought I was hearing. Okay, C1. Second? No E. Cosine. See, the E part would have been your real part, and that's a 0. Just said that. That goes, okay. Since you only have imaginary part, that would be cosine x plus C2 sine x, and normally we would then do same thing for minus, wouldn't we? We do plus C3 cosine minus x, right? Plus C4 sine minus x. I planned ahead real good. No, okay, no. Except that, guess what? Cosine minus x is the same as cosine x. Because it's even function. So that's not linearly independent. And sine of minus x is minus sine of x. So that's not linearly independent. So that's not a good idea to do there, because both of those can be expressed otherwise. So where are we going to get? We need 4, don't we? Fourth order differential equation, you got to have 4 constants. So what will we use? Oh my goodness. Any ideas? Aha, that's it. Just like we did before, put an X in. Okay? So that'd be C3x cosine x plus C4x sine x. There we have it. Okay? So C1 cosine x plus C2 sine x plus C3 x cosine x plus C4 x sine x because of multiplicity. Okay. Now, all right. And then they really expand on this, and it's doing what you just did. If you have multiplicity, just keep adding x's, as many of those as you have. They really went overboard with trying to fill in more blanks. Now, so far, we've dealt mostly with we've dealt with rational roots before. Of course, the most difficult aspect of solving constant coefficient differential equations is finding the roots of auxiliary equations of degrees greater than 2 that we just said. Something we can try to do to test the auxiliary equation for rational roots, and I don't know, do y'all remember the rational zero test? Probably not, okay? Let's review that now, okay? And this is where I got my little technique for checking one first, okay? And by the way, I forgot to notice how they did it. Yeah, they did the same thing. They did. It should be apparent from inspection back on example 3 that m equal 1 is a solution. They did the same thing I did. Okay, let's erase and do this one. This one, I almost guarantee you won't be able to do that easily. 3y triple prime plus 5y double prime plus 10y prime minus 4y is equal to 0. Okay? What's your first step? Second? Okay, you're probably answering right, I just can't hear you. Auxiliary equation, what would that be? 3m cubed plus 5m squared. That's a 10, sorry. You're making fun of my writing again. That's okay, it doesn't bother me too much. Okay. 10m minus 4 equals 0. Okay? Now, this of course comes from y is equal to e to the mx. That's where those m's came from. That's our assumption. Constant coefficients, that's what we use. Now, my little trick that I did before, let's first just see if m's equal to 1. No, it isn't. Okay? Can't be 1 because 3 plus 5 is 8 and 10 is 18 minus 4 is not 0. So that one's not going to help us much. I don't even think a minus 1 would help us either. So, nope. All right, so now we do what they call the rational zeros test. And you may have had this in a pre-algebra course, pre-calculus algebra course, but you may not have. I don't know if you even took one. Frankly, I'd never heard of it before I taught a pre-calculus algebra course, because I never had a pre-calculus algebra course. So this was sort of a new thing for me. Here's what the deal is. You know that if there are rational zeros from that thing, and I'm not going into the whole theory, they're going to be in the form of P over Q. That's what we mean by rational numbers. Okay? Where the P, by the way, and this just happens to be true, is some factor of your constant term. So that could be, what are the possible factors for 4? plus or minus 1, plus or minus 2, and plus or minus 4. Those are all your options for your P. The Q is going to be all the possible factors of your constant, your leading coefficient, which is 3, which is plus or minus 1 and plus or minus 3. Okay? Now, what they suggest you do is write down all these possible rational zeros. And I like to do the integers first, plus or minus, because you put each of these over 1. So plus or minus 1, plus or minus 2, plus or, yuck, I can't write. Plus or minus 2, plus or minus 4, and then start with the fractions, plus or minus 1 over 3, plus or minus 2 over 3, and plus or minus 4 over 3. Believe it or not, those are all the possible rational zeros you can have. Now, I like to do one other thing before I get to going too heavily on this. There's another little technique that hopefully you learned in pre-calculus algebra if you took it. But if you didn't, you may still have run into it. It's good old Descartes' rule of signs. Remember how that goes? Okay. You count your number of sign changes. No sign change there. No sign change there. One sign change. That means you have guaranteed one real positive root. Okay? It may not be rational. It's a real root. Hopefully it's a rational root. You will have one positive real root. And then the other part of Descartes' rule of signs is consider f of minus m. That would be minus 3m cubed. But when you put a minus m in here and you square it, that stays a plus 5m squared. But that changes to a minus 10m and minus 4. Okay? Now count your sign changes. One sign change, another sign change. None there. So that's 2. Okay? So the first one tells us one positive real root. Okay? This tells us 2 or, unfortunately, 0 negative real roots. Okay. Now, how does that help us? Okay? Well, number one, if we do find one positive real root, stop looking at the positives. Only consider negatives. Or, if we do find one negative real root, that means you got to have another one, because you can't have one, only one. It's either going to be 2 or 0. Okay? So, and this is where I learned the little technique of testing for 1. We've already tested for 1. It doesn't work. Okay? So, what I do next is take the negative one. I'll just like small numbers. Put minus 1 here and do our synthetic division. What do we put inside the house? Okay? I'm going to keep it from being confusing. I'm going to erase this part, because that was just using Descartes' rule of sign, but I'm going to leave the results there, okay? Because I don't want you to get the function confused. Okay, what goes inside the house? Synthetic division. We just did it. Help me. 3, 5, 10, negative 4. Do we have enough numbers? Yes. The degree is 3. You need 4 numbers. We got it. Then you do what? Skip a line, draw a line. Okay, that's my rule. Bring down the 3. Now what? Now what? Negative 3, 2, negative 2, 8. No way. No way you're going to get a 0 over there. So negative 1 is not. So positive 1 is not, negative 1 not. Let's go to the next one. Okay, so I'm going to erase. See, I've got magic eraser here. I can do this easily. You got to work at it, don't you? Okay. Now, let's put a 2 in. See what works. Where do we go from here? 6. Continue. Continue. 11. 22. 32. 64. 60. Now, I knew that wasn't going to work. I did this for a reason. Here's the reason. Notice the signs of these. All positive. You put any bigger number here, they're going to even get more positive. No chance of getting a 0 with anything greater than 2. None whatsoever. So therefore, wipe out the +4. So the +2 doesn't work, and the +4 doesn't work. Okay. I should have done that with the 1 too. No, we didn't do 1. Okay. We'll come back to that. Okay. So let's try then -2, and let's see if that will work. So we'll wipe out these and see if we get anything. Continue. -6, -1, 2, 12, -24, -28. Now I did that for a reason too. If with a negative here, you get alternating signs down here, you know you've reached the max, because anything more negative, they're just going to get bigger and bigger, still alternating. So don't even mess with the 4. +2 didn't work, -2 doesn't work, and +4 you know won't work, and -4 you know won't work. Don't go any more positive or negative. So now we're stuck with our fractions. I was afraid of that, okay? So let's start with how are we doing? Yeah. Okay. Where you want to start? 1/3? What does that give you? 1, 6, second 2, 12, second 4, 0. Ding, ding, ding. We finally got a winner. Okay? X equal 1/3 is a root to that equation. Okay? So X equal 1/3. Now, go back up to Descartes' rule of signs, and what does that tell you? You only have one positive real root. There's a positive real root. Don't mess with 2/3. Don't mess with 4/3. Okay? Descartes' rule of signs says you don't do it. So we leave off the plus here and the plus here. May have minus, but not plus. All right? Since that, okay. The other good thing this does for you is this. You've now got a quotient here, and what does that represent? 3x squared plus 6x plus 12. All right? And by the way, don't go up to 2, well, we already know that. Okay. And that also can be set equal to 0. And what's an obvious thing you can do to it? Factor. Okay, and how would you factor that? Divide everything by 3. Okay, so that makes that a 2 and makes that a 4. So now we have x squared plus 2x plus 4. Okay? Equals 0. What you think on that one? Second quadratic formula, for sure. That would be, why did I put x's there? I'm so used to x's. These are m's. Remember? And you let me get away with it. Those are m's. M squared, M squared, and M. Okay. Oops, I didn't erase that one. All right, so the quadratic formula tells you that M is equal to -2 plus or minus the square root of 4 minus 8 over 2. Okay, which would be -2 plus or minus square root of what? 2. Okay, went on and did it. Good. Okay, plus or minus 2i over 2, which is -1 plus or minus I. All right. Now, what does that tell you? Say this again. Okay. So, okay. And by the way, I did it up here too, and you let me get away with it. Okay? This is an M, not an X. Okay? All right. All right. Now, a couple of things. And what you said was right, but a couple of things. Notice here we either had 2 or 0 root, negative real roots. We wound up with 0 because we got 2 complex roots. So don't keep looking. As soon as you do this, of course, you stop and say, no, there aren't any more. Okay? So, were you starting to give me the general solution or a part of the general solution? Okay, general solution. That's going to be something on the order of y is equal to C1 e to the what? 1/3 x. Okay, x over 3, that's good. Plus okay, exactly. I started to write my C and I realized, no, I don't need the C. I need my E. Okay? And that's going to be e to the -x times C2 cosine x plus C3 sine x. There you have it. There is your general solution for that differential equation. Y is equal to C1 e to the x over 3 plus, oh, wait. Oh, yeah, I got it right. E to the minus x times C2 cosine. Whoa! Where did they get square root of 3? They kept that 3 in there for some reason. And is that...
We factored it wrong.
We did?
Yeah, it's 4 minus 16.
Oh, 4 minus... Why did you tell me that, huh? Okay, sorry about that. I wasn't doing, I was listening. Okay. So, that's 4 minus... I've lost my... There it is. No, there it is. Yeah. 4 minus 16. 12, yes. Okay. I can't get the pen to come back. Okay. So that would be 16. So that would be... Okay. Wait. I can't... Okay. So that would be a minus 12. And that would be... Yeah, 2 root 3. 2 root 3. And then the 2's go out. and you have minus 1 plus or minus root 3i. But I like to write it I root 3 because I don't like to put the root 3 in front. So your e to the minus x still worked, and this is a square root of 3x and a square root of 3x. Okay, good deal. Sometimes I even write that as x root 3 for the same reason. Yeah. All right, then they have a little blurb, use of computers. You're certainly welcome to use computers. Okay, they talk about Mathematica and Maple. We don't have either one, but if you do at your school, they have some good stuff you can do with that. Now, they give you another one, 4.137, fourth derivative of y with respect to x, plus 2.179, third derivative, stuff like that. You're going to have computers for that. There's no way you're going to factor that. You're going to find rational zeros, because that all depends on integral coefficients. So I don't know why they put it in here. Okay. So 4.3, but the good news is they didn't put one of those remark sections in. They put in that instead. All right, homework exercises 4.3, any of the odds 1 through 13, any of the odds 15 through 27, any of the odds 29 through 35, and either 37 or 39, or both if you choose. Do 41, and I would say, well, let's just do any of the odds 43 to 47. These are kind of matching type problems. So I'll let you decide what you want to do with that. That's through 47. Then any of the odds 49 through 57. Usually the discussion problems do not have answers in the back. If you find some that do, you can do them. If not, you don't need to worry with it. Okay. Now we're ready for 4.4. And even the name is a little ominous, isn't it? Undetermined coefficients. Okay. And this is called a superposition approach. Now this book uses two different approaches here. 4.4 is superposition approach, and 4.5 is the annihilator approach. Do any of you have any idea whether your school prefers one or the other? I've taught both of them. I find them fairly equivalent. I think I found that the superposition approach kind of makes a little more sense. So unless one of you said, no, we use the annihilator approach, let's do it, I'll be glad to do it. Like I said, I've taught both of them. But I think my personal preference was the superposition, because it's a lot like the other things we've been doing. So, anyone have a preference for the other? No? Okay. Let's go on and do 4.4. That means we'll skip 4.5 and go on to 4.6. I think we may have time for that. We'll see. So, what we have now is a non-homogeneous linear differential equation. And I believe it has constant coefficients. It does. So here's the generic form now. It's much like what we've been dealing with. A sub n, y, the nth derivative of y, plus a sub n minus 1 times the n minus first derivative of y, plus a sub n minus 2 times the n minus second derivative of y, plus ... down to including a sub 3 y cubed, y triple prime, plus a squared y double prime, plus a sub 1 y prime, plus a sub 0 y. Okay, that looks like what we did last time. Here's the difference. That's equal to g of x. Now, notice the function on the right-hand side. All our coefficients, constants only. Our function on the right-hand side could be a function of x. Good news, it can't be a function of y also. If it is, a nonlinear differential equation. But as it stands, that is a linear, nth order differential equation with constant coefficients, but it's a non-homogeneous because it has something to the right. Now that could be a constant. It just can't be zero. If it is zero, that would be a homogeneous. Okay. Said back in sections 4.3, we saw how to solve these when the coefficients were constant. Our goal in the present section is to develop a method for obtaining the particular solutions. And that's what I was saying back in whatever section that was, 4.3 or before, is they keep telling you this is a particular solution. How did they come up with it? That's what we're going to be doing now. So the first is this method of undetermined coefficients. Okay? The first of the two ways we'll consider for obtaining the particular solution y sub p for a non-homogeneous differential equation is called the method of undetermined coefficients. Underlying idea behind the method is a conjecture about the form of y sub p, which is basically an educated guess, okay, that is motivated by the kinds of functions that make up inputs to that function g of x. That's what we're trying to figure out. The general method limited to linear differential equation, such as when the coefficients are constants, and g is also a constant, or a polynomial function, or an exponential function, or a sine or a cosine function, or a finite sum or product of any of those functions. So basically we're going to limit our g. G of x can be a constant. That's fairly straightforward. A polynomial. Okay. An exponential. Sine or cosine. Or any finite sum of any of the above, everything above. Constants, polynomials, which would have constants in them, e's, exponential functions, sine or cosine function. Notice what we don't have in this list. We don't have rational functions. We don't have log functions. We don't have any of the other trig functions or hyperbolic functions. So hyperbolic functions can be done as e's, but we don't worry about those. Treat them as e's. Or we can have combinations of these. Okay? Now, strictly speaking, g of x equal k, a constant, is a polynomial function. That's why I said those are included there. Since a constant function is probably not the first thing that comes to mind when you think of polynomial, our emphasis is that. Okay. So, they're going to give some examples. That g of x could equal 10. That would be a constant. X squared minus 5x. That would be a polynomial. Then they go to finite sums of these. Something like 15x minus 6 plus 8e to the minus x. Okay? That would be a combination of an exponential function and a polynomial function. Okay? Or sine of 3x minus 5x cosine 2x. Okay? All right. That has a sine function and then a... Now, wait a minute. Okay. I said finite sums or products. I forgot to put that in. Sums or products of any of the above. So that's where the 5x times the cosine 2x is okay. Okay? And then another g of x could be x e to the x sine x plus 3x squared minus 1 times e to the minus 4x. Boy, you're getting complicated here, but it's perfectly fine. Any sum or product of any of the above. Here's a product of a polynomial, an exponential, and a sine or cosine. Added to, and a sum will work to, a polynomial times a exponential. Okay? Are we going to do ones like all these? Probably not. We'll do some simple ones, but you'll see how to combine or add or increase those. Okay? Now,
I think we're out of time.
oh, we're out of time. Shucks. Okay. So we'll begin next time on, we'll probably review a little bit of that right there. And we didn't get far enough to any homework exercises here. Now this is a long section, okay? So it's going to take most of next time and maybe into the following time, but I hope that I'll be able to at least start with variation of parameters. Sometimes I do and sometimes I don't. We'll see. Have a good weekend. Of course, working on research papers and tests. That'll make it good, won't it? Good deal. Okay. Now, let me stop this.